All right, so today we're going to talk about tangent planes and normal lines. And we spent the last couple of lessons talking about the gradient and how it relates to level curves of a function. So if we have, just a kind of a recap, if we have z equals f of x, y, and that equals a constant, then the gradient, these are level curves, and we figured out yesterday that the gradient is normal to these level curves. If we have a function, some function of x, y, and z, and this equals a constant, this is a level surface. And today we're going to be interested in functions of the form of this form. So we're looking at f of x, y, z equals some constant. So let's assume that we have a function in this form. And we're going to let r of t be some position vector of a curve on the surface. So r of t is just a vector valued function that describes a curve on the surface. We've talked about these. We talked about these earlier in the chapter. And we're going to describe r of t. We're going to say that r of t is, we're going to write it is in its component form, is some function of x times I. So some function y of t times j plus z of t times k. So this is our position vector in component form. And we have f of x, y, z as a constant. So we're going to use the chain rule. We want to find df dt. Now f is a function of x, y, and z, and x, y, and z are a function of t. So we can use our chain rule to say that df dt equals df dx times dx dt plus df dy dy dt plus df dz dz dt. Our chain rule tells us this is what df dt is. Now since we have f of x, y, z as a constant, what is this derivative? 0. So this equals 0. And if we look at the form of this expression right here, what does this look like? This looks like a dot product. This is del f dot dx dt, dy dt, dz dt. This is del f dot r prime of t. So the gradient, the dot product of the gradient with this should be r prime, the dot product of the gradient and the velocity vector, if we think of this as a position vector, this is our velocity vector, is 0. What does that tell us about the gradient and our position vector, our velocity vector? They're orthogonal. So del f and our position vector are orthogonal. So we can write our conclusion here is that if at some point x0, y0, z0, that del f at x0, y0, z0 does not equal 0, then del f at our point and we're going to say that this is at some point x0, y0, z0 is at time t0, this equals 0. And the gradient is orthogonal to the tangent vector. And we didn't put any restrictions on our function, and our position vector was an arbitrary position vector of an arbitrary curve on our surface. So we can say that this holds for any surface and any curve on the surface. So our gradient, this tells us that our gradient is orthogonal to the surface. Our function and our position vector were arbitrary, so our gradient is going to be orthogonal to the surface at any point. So del f is orthogonal to our surface at any point. So if we want to find a normal vector to our surface, the gradient gives us our normal vector. So this gives us several pieces of information. Any questions before we go on? So I'm going to head this. This is del f as a normal vector. So this is important because, one, del f, what we just concluded, is normal to f at any point. we can use del f to find our tangent plane. The plane normal to del f is the tangent plane to our surface at that point. So the gradient del f gives us our normal vector to our tangent plane. And the line through so the line through the point, we're going to call it P0, where del f of P0, at del f of P0, is the normal line to the surface. So del f gives us a normal vector. From the normal vector, we can find a tangent plane at any point, and we can also find a normal line to our surface at that particular point. And the idea of a normal vector to a surface is an important idea that we're going to use a lot, especially in chapter 15. So let's draw a picture just to get a geometric idea of what we're talking about, a graphical idea of what we're talking about. If we have our surface here, here's our surface. Here's our curve on our surface. This is r of t. This tangent vector is going to be r prime of t. And del f is going to be here. And this is f of x, y, z is a constant. And we'll say equals 0. That's a right angle, and this is our point P0. So del f is normal to our surface. It's normal to our tangent line through, and our position vector r of t is any arbitrary curve on our surface. So that's our picture. Questions? So a couple of different ways that we can write our normal vector. We can express our normal vector in several ways. We can say that n, our normal vector, is the vector df dx, df dy, df dz. Or we can, the other way we can write it just in our different expression for our partial derivatives, f sub x, f sub y, and f sub z. And if we have a function of two variables, if we have our function in the form z equals f of x, y, to find our normal vector to our surface, we want some function of f of x, y, z equals a constant. We can write f of x, y, z equals f of x, y minus z. And our normal vector to that surface is just going to be df dx, df dy, and negative 1. So if we have a function of two variables, if we have our function written as z equals f of x, y, we just rewrite that as our function of three variables, whatever f of x, y is minus z. And that gives us our function f of x, y, z is a constant. And this is going to be our normal vector. So the normal vector gives us the direction numbers to write the equation of our tangent plane. So we're interested in our tangent plane in this section, and we're also a little less interested, but still interested in the normal line. The tangent plane is going to be the more important quantity that we're looking for. So if these are the direction numbers to our normal plane, then to our tangent plane, these are our direction numbers. The equation of the tangent plane will be, and we're going to say at P0 equals x0, y0, z0. F sub x times x minus x0. This is our standard equation of a plane, plus f sub y, y minus y0, plus f sub z times z minus z0 equals 0. So this will be the equation of our tangent plane. And if z equals f of x, y, if we have our function expressed this way, then the equation is f sub x, x minus x0, plus f sub y, y minus y0, minus z minus z0. And that will be the equation of the tangent plane.
Did you mean z equals f plus y?
Yes, that should be f of x, y. Thank you. So this is kind of nice. I like the idea of a tangent plane. It brings together it's a lot like the heat-seeking particle problem. It brings together a lot of things that we've talked about. We've talked about the gradient, we've talked about surfaces, and we've talked about the equation of planes. And we'll talk a little bit more, we'll do an example, we'll talk about the symmetric equations of lines. So this brings together lots of the concepts we've talked about so far this semester. The idea of the gradient of tangent planes and how we write the equations of planes and the equations of lines. Any questions? All right, let's look at a couple of examples. First off, we're going to say that for these, f of x, y, z equals 0. We want to describe the level surface for f of x, y, z equals 0. So for my first example, we have f of x, y, z equals 3x minus 5y plus 3z minus 15. What is that surface? What is the level surface that this describes? So we're in 3 dimensions, so it would be a plane. We have it's a linear relationship in all 3 variables, so this is a plane. So the level surface f of x, y, z equals 0 for this particular f is a plane. How about f of x, y, z is x squared plus y squared plus z squared minus 25? Sphere, right? And the radius is 5. So this is a sphere with a radius of 5. How about 4x squared plus 9y squared minus 4z squared? We want to describe the level surface when f of x, y, z is 0. It's an elliptical hourglass. Are the sides straight or the sides curved? Sides are straight, so this would be a kind of elliptical shaped cone. So if I write 4x squared plus 9y squared equals 4z squared, and I look at just the relationship in any coordinate plane, I'm getting a line. Take the square root of both sides, I get a line. So this is an elliptical cone. And the last one that we'll look at like this. Our function is 16x squared minus 9y squared plus 144z. And we're saying that equals 0. So if we look at the y in the yz plane, we get a parabola, right? Parabolas. If we look in the xz plane, our signs are opposite, so we get a hyperbola. So this is a hyperbolic paraboloid. That's that saddle shape. So you guys having a good discussion about the parabolas? Right? Up like a cup, right? Down like a frown? All right. Let's look at some examples of actual calculations that we all like to do. I'm sorry, we all want to do, right?
It's our only purpose in life.
Right. So we have x squared plus y squared plus z squared equals 11. So we have a sphere, and we want a unit normal vector at the point 3, 1, 1. So our desire is to find a unit normal vector at this point. So we know that del f gives a normal vector. We have our function f of x, y, z as a constant, so del f is going to give us a normal vector. So if we calculate our gradient, what is our gradient? 2xi, 2yj, 2zk. And at 3, 1, 1, del f is just 2i plus 2j plus 2k. Oh, 6i, thank you. Say that darn arithmetic. So that's a normal vector. We want a unit normal vector. So the length of del f is the square root of 36 plus 4 plus 4 is the square root of 44 equals 2 square root of 11. So a unit normal vector, I'll call it u, is 1 over 2 square root of 11 times 6i plus 2j plus 2k equals 1 over square root of 11 times 3i plus j plus k. So there's our unit normal vector at the point 3, 1, 1. So del f is nice in that it gives us this unit normal vector. Now let's calculate our, the equation of a tangent plane and the equations that represent the normal line. And that'll be our last example. So we have x squared minus y squared plus z squared equals 0. And we want the equation of the tangent plane and the normal line, and we want symmetric equations at the point 5, 13, negative 12. So we know that the gradient, that del f, gives us our normal vector. So we need to calculate our gradient. So del f of this function is 2xi minus 2yj plus 2z plus 2zk. And at 513, negative 12, del f is going to give us 10i minus 26j minus 24k. So this gives us the direction numbers for our plane. Our direction numbers are A equals 10, B equals negative 26, and C equals negative 24. We could divide everything. We could use any multiple or any multiple of these. We'll just use these. So the equation of our plane and equation of our plane is 10 times x minus 5 minus 26 times y minus 13 minus 24 times z plus 12. So there's an equation of our tangent plane.
Shouldn't it be plus 13?
This is, so it's x minus, or y minus y0, and y0 is 13. That's our point. And del f is parallel to the normal line. So del f is the direction, is the vector parallel to the line that we're interested in. So we can write the symmetric equations of our line. Do we remember what symmetric equation of a line, of symmetric equations of a line look like? X minus n's got it, x minus x0 over a equals y minus y0 over b equals z minus z0 over c. So our normal line is x minus 5 over 10 equals y minus 13 over minus 26 equals z plus 12 over minus 24. So that would be the symmetric equations of the normal line. And if we needed to, we could write the parametric equations as well. Questions on that? So from this particular section, that's our two main goals: to find the equation, to find a normal vector to a surface, to find the equation of a tangent plane, and to find the equations of the normal line. The idea of a normal vector to a surface is going to be a big one when we get to the end of the year. We'll use normal vectors for pretty much everything we do. All right, homework. Because we want our homework, right? No, these are all ones that we want to do. And the other one, if you did it, it was still good. It's still a good problem. It's just because doing math is always better than not doing math.